Okay, here we've got another differential equation that involves a rectilinear motion here, and we're given an acceleration. Okay, the funny thing in this case is we're not really given the acceleration; we're more of given the initial and final velocities. And so, but it also lets us know that the acceleration is constant. And so, since we know that it's constant, we can basically use the slope formula to find the acceleration given the final and initial velocity. So it's final velocity minus initial velocity divided by final time minus initial time. This is going to be your difference quotient. Okay, and so I went ahead and did that. I I didn't like how everything was in miles per hour and seconds. Okay, and so what I decided to do is I put everything in feet per second. Um, in the end, because actually the final answer wanted it in feet anyway. So I took uh, this thing here, the 0 and the 60 miles per hour, and I changed it to 88 feet per second. Okay, so then I used that and giving me an acceleration of 17.6. Now you can treat this as a differential equation, and you integrate this twice. Okay, when you integrate this twice, you end up getting basically this, which is the s of t. Okay. Now I happen to remember that if you have a constant acceleration, um, then you're always going to be dealing with a scenario where you end up with a second degree polynomial. Okay. Your acceleration is sitting right there. Your initial velocity is sitting right there. And your initial position is sitting right there always. Okay. They tell us that it accelerates from rest, right? And so I'm kind of guessing that my initial position is going to be 0 and my initial velocity is also going to be 0. I'm basically making that assumption here. So if that's the case, this v of 0 becomes 0. This s of 0 becomes 0. I toss my acceleration down right there. And this is where the 5 comes in. Basically, I'm evaluating the position function at 5, where I know I have an initial velocity of 0 and an initial position of 0. Okay. And essentially, you're just getting your classic 1 half at squared formula. Those of you in the physics realm would know this one pretty well. And so you end up getting 220 feet. Okay. And that's how that one is. Took a little bit more of a physics approach to this, classical mechanics, rather than a differential equations approach.